Hello, everyone. Welcome to December's performance virtual chapter meeting. Looking forward to today. We've got a great webinar ready for you. Next, I'm your moderator today, Leslie Weed. Our performance chapter Twitter account is here. Our hashtag website. We will post the videos post-hand. You can navigate to them through the website and also find some of our future meetings there. We have a discussion list and email. If you are interested in speaking for one of the future webinars, please reach out to us. We're always looking for speakers. So onwards. For if you have not joined a webinar before and go to webinar, just a couple quick tips. If you do require assistance and are having any issues, please feel free to raise your hand and I will do a direct chat with you to help you work through any issues you might have. You can maximize your screen. There is a little icon at the bottom. And then questions. So our speaker today, Bradley, will try to answer questions as he's going through the webinar. So feel free to type in questions there. That's not gonna, he will see those as best as he can and answer them as we go along. And we will try to wrap up with some questions at the end also. Audio is only available through your speakers. There is no dial-in numbers, just as a reminder. Okay. So our sponsor is SolarWinds. They have been a fantastic sponsor for our chapter. Somebody today will get a $100 Amazon gift card that has participated. So we really appreciate SolarWinds' generous sponsorship. This really helps us do a lot of things with the chapter. Okay, our presenter today, Bradley Ball, very excited for this. Indexing internals for developers and DBAs. So I'm going to go ahead and make him our presenter. And he's going to take it away. Thanks.
Thank you very much. Okay, let's see. Let me make sure that I get the right one. Okay, and let me know when you can see my screen.
Looks good.
Excellent. Thank you, everybody. This is not the Past Summit 2015, but I did do this presentation for the Past Summit 2015. So if you online, and you can actually view it at the Past TV website if you'd like to see the whole thing. We're not going to include a couple portions, the portions on clustered indexes, on clustered column store indexes. We will be talking about clustered indexes, but clustered column store indexes will be online. So we're not going to hit that today. Our subject is indexing internals, DBAs, and developers. Just a quick moment. You're here at a PASS virtual chapter. There's a lot of other things that are available at PASS. I encourage you to get involved in the community. Those people that work for me that I have here at Pragmatic Works, I see the most personal growth in people when they are active in the community. Nothing gets you to know a subject like it does when you become a presenter or you get involved. So a lot of wonderful ways you can do that through local user groups, SQL Saturdays, attending the 24-hour PASS, volunteering to speak at virtual chapters. There's a lot of wonderful things you can do. We're not going to spend a lot of time on this. You're probably familiar with me. I am very lucky to be a SQL Server MVP. Cool things I've done before. I've been a DBA for the U.S. Army and the Executive Office of the President of the United States. I'm currently the Data Platform Management Lead for Pragmatic Works. What that means is I get to work with a lot of really brilliant people covering the stack from the database engine to the cloud to working with APS and SQL Azure Data Warehouse, big data, and Hadoop, Cloudera, all that good stuff. You can find me on Twitter at SQLballs. You can find my blog at SQLballs.com. I know that is an incredibly difficult to remember name. You probably will never be able to remember that. Very long, too. My email is bball@pragmaticworks.com. Please feel free to shoot me an email if you have a question. It may take me a little while to get back to you. I'm currently weeding out of about 250 emails, but I'm hopefully going to be through that by the end of the day. And here are the 2 books I've written on. All right, here's what we're going to talk about. We're going to talk about classic structures, clustered indexes, heaps, non-clustered indexes, how to measure performance, making good changes, avoiding mistakes, and we're not going to be able to make it to the column stores today. So we're going to try to have a little bit of fun. I promise you, I'm going to do my best. This won't be lame. So index types. We want to talk about covering indexes, clustered indexes, heaps, non-clustered indexes, which include filtered, covering, and unique. Column stored indexes, remember, I can answer questions about those if you have them, but we're not going to cover them in depth. We're not covering in-memory OLTP indexes, full text indexes, XML indexes, or spatial indexes. If you're interested in those, Denny Cherry does a lot of great presentations and blogs about XML. Jason Strait does a lot of good stuff on XML. Caitlin Delaney has a free in-memory OLTP deep dive book. You can get the PDF for it at SQL Server Central, or you can send your favorite author 59 cents by purchasing it for about 20 bucks. It's a fantastic read, and I recommend that. That will get you everything you need to know about those. We're going to focus right on these three right up here. So first, let's cover classic structures, clusters, heaps, and non-clustered indexes. So we're going to hit everything a bit later, and I know there's a lag in my slides coming through, so I'm just trying to let this go before I go off the agenda. So next up, we've got heaps versus table. Now this sometimes seems to be a little bit of a holy war, and the main reason for this is anybody who has ever worked in Oracle has been told over and over again the default table type they should use is a heap, and that is true for Oracle. In SQL Server, we often hear you should use a clustered index, and the clustered index is the default table type that is recommended for SQL Server. So it gets to be a little bit of a holy war, but it's really not that complicated. The key thing we need to do is understand when we should use each, and that's going to be determined by our workload and what we're trying to accomplish using SQL Server. There's no rule for one size fits all, and I hope to give you a couple examples in here just based off of work experience and what I've seen out there in the field to be able to disprove both of those theories. So first, what we're going to do is we're going to discuss what a heap is. Because we have structures within SQL Server. We have a base physical object, and that base physical object is either a heap, which means the data is collected in an unordered type, or we have a clustered index. We'll get to those in just a moment. So like that desk right there, a heap is a bunch of unordered pages. If I wanted to find something on that desk, sorry about that, if I wanted to find something on that desk, chances are I would have to look through the entire desk. Probably not going to find something just by reaching down and picking it up unless I get lucky. The way I often tell people in a class to think about a heap is imagine I take the phone book and I unbind it from its hinges and I throw it up into the air, and while all the pages are sitting there floating down slowly, I say, find Bradley Ball. Well, you don't know if Bradley Ball's in the white pages, if he's in the yellow pages, if he has an ad taken out and he's on some other random page. You don't know if there's 20 of us living on a city and you've got to get more unique information than just Bradley Ball. Maybe there's 5 of us to return. You don't know. You're going to have to search through every single page that I just threw in the air. And that's the same thing with a heap. The pages are linked. It's still a regular table. And they even have statistics, but their order is not guaranteed. And every operation that SQL Server performs against a heap is a scan, which means we have to scan the entire physical object. And that's where they sometimes become unnecessarily complicated. When we look at them from an internal perspective, SQL Server, remember, it's just a C++ application. It's something that programmers have to sit up in Redmond and build for us. And the way we actually structure a heap is we have index allocation maps, IAM pages, that collect these page chains together to be able to tell us all these pages are collected within this heap of information. But that's the only overhead structure that we really have when we create a heap. That makes heaps very, very powerful. So letting my next slide load, what we're going to do is we're going to talk about where heaps are useful. Heaps are useful for a few situations. Loading staging tables. If you're in a business intelligence environment and you need to load data very, very fast into a staging table, you are not going to be able to load that data any faster unless you do it in a heap. Heaps are fantastic. One possibility on SQL Server 2014 is throwing it into an in-memory OLTP table, but as we all know on 2014 there are some limitations on data types. Those limitations on data types are going to get a little bit better for us in SQL Server 2016, but for the most part, Right now, if I need to just take a lot of data and slam it into a table very, very quickly, I'm going to create a heap. Temp tables. Most of the temp tables I've ever used, I don't put a clustered index on. You can. You can put clustered indexes on them. You can put non-clustered indexes on them. You could even compress a temp table. But most of them are just heaps. I do an insert into, or I throw data into there, so that way I can do some type of aggregation with it and pull it out. Heaps are incredibly useful for this. One thing that I don't have listed up there is if I have a fact table in a data warehouse, probably going to be a heap. I may have a unique index on there, but I'm probably going to have it be a heap, so that way it just loads that much faster. Now, if I get my choice, clustered column store, but that is a place where if I'm on 2012 and earlier and I don't have the chance to use a clustered column store, I'm probably going to make my fact table a heap. Some issues. You could have poor performance, particularly if you're trying to do one-row seeking operations. Forwarding pointers. Forwarding pointers can cause a little bit of overhead as well. So what is a forwarding pointer? A forwarding pointer occurs if I take a data page and let's say I fill it up completely, and in my table I've got a varchar field. Let's say we've got a varchar 5000 and I only put 20 characters in there. Well, then I come back and I do an update and I say update varchar, now let's put 500 characters in there. Well, there's not any room on that page for that variable length field to grow. So what happens is my row will actually pop off of that heap page, and it will go and live on another page. In its place, it will leave a forwarding pointer that points to the new page that that data resides on. The nice thing is that page, that row has a pointer back to that forwarded stub. So if I come down and I read it, I have to do a two-hop operation to actually get to my row. Now let's say that page that it's on now, that new page, it gets completely full, and I do another update operation. And this time I change my varchar from 500 up to 1000. Well, there's no more room for it to stay on that page. It's going to pop out again. The nice thing is we don't leave a trail of forwarding pointers. We go back and we update the location where the new page is on the previous forwarding pointer, and we'll only have to have one hop to get that record. So it's not incredibly inefficient. We're just looking at a couple hops. But if I have non-clustered indexes, say for example I've got my heap fact table and I've got a non-clustered index and I'm doing some lookup operations against that heap table, that could be a lot of jumps that I've got to make because of forwarding pointers. So what are some remedies to this? First off, you could change it to a clustered index if you're looking for one-row seek operations, or you could update and rebuild the table. When you use sysdmdb index physical stats, we're going to cover that later when we talk about fragmentation, you can see the fragmentation for a clustered index. You can also see the number of forwarding pointers on a heap. Since SQL Server 2008, the rebuild command has been available for heap. It's not available in 2005 and before. That was something that came about with the advent of compression in SQL Server 2008. In SQL Server 2005 and below, your only option to get rid of forwarding pointers is to actually put a clustered index onto the heap and then drop the clustered index. Next up, let's actually talk about clustered indexes. So your eyes aren't playing tricks on you if you're seeing this slide. That is an upside-down tree. And the reason is we have an upside-down B tree that we use for our clustered indexes. A clustered index, keep in mind, if you're ever in an interview and somebody asks you how many clustered indexes you can only have one per table. Pretty simple one right there. A table is either a heap or a clustered index. Remember, those are our two options in SQL Server. The second we put a clustered index, I am going to physically reorder and reallocate the pages that this data is stored on. And I'm going to logically store it in that order. And I say logically because it could get physically out of order a little bit, but you'll always have logical pointers in your clustered index that tell you exactly where the data is so you can find your individual rows. A clustered index can utilize seeks and scans. When we use the DMV sysdmdb index physical stats, one of the things you'll notice is that the index level 0 is, well, it's always there. You could get 1 and higher, but 1 and higher is going to be that upside down root structure. 0 is where your physical data actually resides. I only want you to care about your fragmentation at level 0. That's the most important one. If you have white space in your intermediate and your root pages, it could give you a false reading of fragmentation. It may look like it's 20% fragmented. And it doesn't matter how many times you rebuild it, I'm just not using all of the space on that data page. It's going to give me a false reading. So I only want you to care about level 0's fragmentation when it comes to knowing how I want to maintain my indexes, whether I'm rebuilding them or whether I'm going to reorganize them. Couple best practices around clustered indexes. Best practice for a key for non-clustered indexes, you want a for a clustered index, is you want a clustered index to be narrow, static, unique, and ever increasing in value. My favorite clustered index key is an integer. 4 bytes, an integer, you can increment by 1, sit there and go up to positive 2.4 billion some odd values. Now, if you've ever run out of an integer before, it is a very painful event. I have done this, and what happens is the table actually stops, and you cannot insert anything else into there once you run out of integer values, and you're incrementing by 1. So your question is going to be, what happens in that case? Well, I've got to change my data type, and I've got to wait as I update all of the columns in that table. Obviously, it's a very heavily used table because I'm using and I've inserted over 2.4 billion some odd rows. Now, a couple tricks that you can use. First off, if you know you're going to use an integer value, there's a positive integer range. There's also a negative integer range. We have positive 2.4 billion some odd values. We also have negative 2.4 billion some odd values. So if you're going to increment by 1, you could start incrementing it at the negative 2.4 billion range, and that will actually get you about 4.8 some odd billion rows to be able to play around with in the integer range. But let's say you know you're going to potentially get hundreds of billions of rows. Well, logically, you want to know what's next. When I was sitting in the room and my boss came to me and I said, well, we should change this from integer to big int, his first question to me is, well, aren't we just going to run out of that? And it's a logical question. We just ran out of this one. I'm saying go only to the next one because the highest integer value that we've got for Microsoft SQL Server is big int. MySQL, Oracle, a lot of other systems have bigger values than big int. All we have is big int. And it's a good question. And I sat down and I did the math one. I said, boss, look, I'm a very hopeful man. They keep making computers faster and faster and faster. If I was able to insert 1 million rows into a system per second and I incremented my identity integer at 1, we have to go several spaces beyond billion. It's something like exadillion data. I made that up, but it's an exa number and it's quite large. Basically, it would take me 239 years incrementing at 1 to be able to run out of numbers. Now, I'm not typically a type of guy to say, let the next guy worry about it, but chances are in 239 years, you will no longer be the DBA or developer at your organization. I'd say it's safe to let the next guy. Hopefully, SQL Server version 2150 will have a new thing other than big int in it. If let's say we have a system that's fast enough that we could run out of those values. If I took a 100-byte row, not even planning for index overhead with this, just 100-byte rows, and I inserted that many rows, I would have 32 petabytes worth of data. It's a lot of data. We're going to need to probably reevaluate our archival system, and we're going to need a bigger SAN. So big int should be good for you. And in the back of your mind, you may be wondering, well, why don't I just use big int to begin with from now on, no matter what? If I'm on a data warehouse, I want to be careful with that. There are some enhancements on SSAS when I'm building cubes that work very well with integers that do not work well with big ints. I would use an integer value on my dimensional tables. If I'm going to put a big int on a table, I'm probably going to put it on a fact table where I know I may get greater than 5 billion rows on it. So there are some nuances to it, but I wouldn't by default always hop to big int. But if I knew it was a system, say an order detail table that I may be doing for an OLTP system, big int's probably going to be my go-to thing. Some issues you'll get with clustered indexes. We're going to suffer from page splits occasionally. Page splits cause fragmentation. Think about our example with the heap. Only now we've got a clustered index. I've got a variable length field. It's a varchar 5000. I've got 50 characters in it. Well, I go in and I put an update, and I update it to 500. We don't have forwarding pointers. The forwarding pointer doesn't split out. What happens is I actually do a logged transaction that is a lop delete split. And what happens is that splits out my page, and it puts 50% of my data on this new page, and it keeps 50% of the data on my old page, and it gives me the room to be able to add that. Those updates and those page splits, though, that causes fragmentation. That causes more pages to need to be read as I'm going through and I'm reading my pages. I had one customer, and the absolute worst clustered index you can have is a GUID. Even sequential GUIDs, not great. Sequential GUIDs are only sequential as long as you never reboot SQL Server. So as long as you plan to never reboot SQL Server, you're good to go. But GUIDs are terrible because the order is completely random. I might as well be putting them in a heap because I'm going to cause a lot of fragmentation, and I'm also going to have to do a lot of scans to be able to get this data. So it's going to cause us a lot of overhead. I had a client that had a system, and they couldn't re-architect it, and their clustered indexes were GUIDs. I had to rebuild that table every single day. And when we talk about fill factor in a moment, I'll tell you what I had to set it to because it was ridiculously low just for us to be able to get through the day. But I used to have to take the system offline during lunch just to rebuild the indexes because it was so bad. Updates are keys. That is the key thing that's going to cause fragmentation for us. So some remedies for this: index maintenance, rebuilding your indexes or reorganizing your indexes, adjusting fill factor. There's two things to remember: fill factor and pad index. Fill factor adjusts the free space that you have on a page. So if I set my fill factor to 80, it means I'm going to fill up 80% of the page and leave 20% blank space on that page. So if I get updates, I can update and expand those rows without having to have a page split. For my client with the GUIDs, I had to set the fill factor for 40. And we left 60% of white space. Now this does require more disk space. I'm making a little bit bigger table, but this was the only thing that allowed us to get through the day without having to rebuild the indexes. That's a very high scenario. I typically don't have to take that, but if I'm rebuilding an index over and over and over again every single day, chances are there's probably some adjustment I can make with fill factor to prevent from having to rebuild that index daily. Pad index adjusts the white space the same percentage as fill factor on my intermediate and my root level pages. Another thing I can do is, let's say I have an orders table. Often I may put, as I'm architecting this, I think it's a great idea, I'll put a big int as my clustered index. The problem that I'm going to get to is that people aren't going to search on that clustered index. They're going to be searching for the orders table by date. And I probably want to change that and modify the cluster key so I'm actually doing a better job of satisfying my user queries. Might not be narrow, static, unique, and ever increasing, but it's probably going to be a sight better for query performance. But I'm going to judge those things as my system gets underway and as I'm looking at them. Next up, what we're going to do is we're going to take a little bit of a look at what that structure might look like. I've kind of architected out a B-tree structure here. I've got my root up top, I've got my intermediate level, and then I've got my leaf level. Remember, the leaf is where I've got my data. This is my alphabet table right here. You can see on my leaves, I've got A and B, C and D, F and G, H and I, J, K, L and N, O, P, Q, R, S, T, U, V, W, X, Y, Z. Now notice the low value from each of my leaf pages goes up to my intermediate page. That's not an accident. The same thing happens for SQL Server. My low value on a page goes up to the intermediate page. So A is up, C is up, F is up, H is up, and then J, O, T, and W. And then the low value from each intermediate page goes up to the root page. A goes up to the root, and J goes up to the root. So let's say I take this and I say I'm going to write a query. I say select all from alphabet where value equals G. I'm going to look at A and I'm going to look at J. I'm going to say G is greater than A, G is less than J. So I'm going to transverse this path. G is greater than A, greater than C, greater than F, less than H. I'm going to transverse this path, and there's G. And I just did 3 reads and I got my G information. That's called a seek. Now, even if I have a clustered index, if I decide I want to say select all from alphabet where letter is between A and S, I'm going to end up grabbing over 80% of my table. Around the 80% mark, I will go from a seek operation to a scan operation. SQL Server is just going to go look at some much more efficient operation for me just to say I'm going to read the whole table in and give you these results rather than constantly going down through root and intermediate page to be able to interact and grab this data. So you will get scan operations with clustered indexes, but you can also get seeks. You cannot get seeks with heaps. Next up, we've got non-clustered indexes that we're going to be talking about. So you can have 999 non-clustered indexes in the current release of SQL Server. I believe they've upped that to over 1,000. Let's say it's 1,024 in PAS v12 right now. That is not a goal, not a goal at all. You can only have them have 900 bytes, same limitation as on clustered indexes. It's got the same B tree upside down structure. We can utilize seeks and scans. At the 0 level, we have the data that we have defined in the key for the index, including any include column data. And we also have pointers over to our physical base table, be it a heap or be it a clustered index. When we look at that, those leaf levels contain either a row ID or a clustered index key, because we have to be able to find the base set of unique data that we're actually retrieving from that non-clustered indexes. Some best practices you want to keep in mind for non-clustered indexes is we want them to be columns and search terms. If you ever hear someone say a where value predicate, or you hear me say it, that predicate value is whenever I say where column equals this column, that column right there. I want a non-clustered index on it. I want to search it. I don't want to have to scan my entire table. I want to be able to get that data quickly. We will typically want to use them as foreign keys. Anytime we've got intersections, to be able to make sure that those integer values we defined as our keys can talk with one another. If we've got them in tables and they aren't part of the clustered index, if we have intersection tables that we're using to be able to join two different systems like customer and customer address, we may have a table because we may have a system like Amazon where we've got multiple customers with multiple addresses and we want to link those together. Any include columns for a covering index. A covering index is basically a query where every single row is satisfied by an index. Now, I wouldn't include every single column that's in a table. That's inefficient. I'm basically copying the base table. And that's something to keep in mind for a non-clustered index. This is a secondary physical copy of the data. It has its own locking structures. Now, if you do a lock on a base table, you can make it to where you cannot get to the non-clustered indexes to access them. But if you have granular locks on your clustered indexes, you're going to be able to get to granular locks on your non-clustered indexes as well. I've actually solved deadlocks before by throwing non-clustered indexes in place. I know some people say they feel dirty when they do it. I think it's kind of awesome to be able to throw out an index and be able to solve a deadlock. I would rather fix the code, but don't get me wrong, I've got plenty of third-party vendor systems where I'd like to fix a lot much more than code. So let's do a demo. This is going to be index internals. This is a demo by PowerPoint, and I know this is taking a little while to load, so I'm hopefully not going to lag too hard to be able to get to people. I'm trying to watch a little bar that I've got that tells me how many people are seeing this. So whenever I get to 99%, I'm going to hit next. A couple things that we're going to be using for this. DBC Commands. DBC IND. This is going to allow us to be able to transverse any index allocation maps. So that way I can find all the pages that are chained together in a table. DBCC page. This is going to allow me to look at the contents of an individual page and be able to see what's going on it. And then DBCC trace on 3604. This is going to send print commands to the SSMS window. Typically when I do a lot of scripts, I can jump around very, very quickly, and that can get confusing, especially when we've got a lag. So I've got all my demos sitting in my slides, so the scripts are up on my blog to be able to grab, but this way you've kind of got a reference guide to go along with it as well. We're going to create a database called demo indexes. The first thing I'm going to do is I'm going to create a pretty basic table called clustered table. I'm going to have an identity column, my ID, incrementing by 1. It's a primary key clustered index. Remember, a primary key is a constraint. It says that I can only have one unique value like this, and I cannot have any nulls. A unique constraint is everything has to be unique, but I can have one null value as well. And then I'm going to do a my char column, varchar 3500. I'm going to replicate A 3500 times, so I'm filling that up. And then what I'm going to do is I'm going to insert into cluster table 2 rows. Then what we're going to do is I'm going to do a DBCC IND. I'm going to take a look at this table, and I'm going to pull back all the pages. I'm going to insert one more row into the table, and then I'm going to do another DBCC IND to see how that has affected things. So here we go. Here's my first DBCC IND. I've already inserted my rows, and as you can see, I've got my page file ID 282. This is an IAM chain, and it's an in-row data type. That's my IAM chain, and it's a page type 10. That means it's an IAM page. 282 right there. That's my IAM page. Page type 1 is my data page. It's 281 right there. I'm going to insert one row, and then I'm going to do another DBCC IND. You can see that I've added to page 282 and 281, page 283 and 284. Looking over here, I see page type 1 for 281 and 284. These are data pages. Now I've got this page type 2 that wasn't here before. This is an index page, and this is an overall root page. So now we've got a root page. Let's take a look at it. I'm going to do a DBCC page, demo indexes, and I'm going to look at page 283. When I get this back, it actually returns it in grid view, very interestingly. The grid view that comes back lets me know that I've got child page 281, child page 284. My ID is null right here. It's 3 right here. Now remember, I told you the load value would come up. So we inserted 3 records. 1 and 2 are on page 281. 3, all by itself, is on 284. So why is this null? Well, it's null because you can do negative infinity. And negative infinity is, I'm sorry, negative 2.4 billion, which kind of gives you this negative infinity. It's the opposite end. So it's null for that low value. I'm going to then insert 3 more values. So we've got 3 on our pages right now. 1 and 2 are on 281. 3 is on 284. So 3 more values is going to give me 4. That should go on 284. Because remember, it was 3,500 bytes for my varchar, and I filled that up. It's 4 for my integer, 3,504 plus some metadata, probably 3,517. I can fit 8,060 bytes worth of data on a page. So just adding those two together, it's a little over 7,000 bytes. I can only get 2 per page. So 1 and 2 are on 281. 3 is on 284. I'm going to add my 4th one here, and then I'm going to get 2 more that are going to go on 284. And that should give me my next page, and 5 should be the low value that comes up. And sure enough, I do another DBCC IND. What I can see is that I've got page 285, and the low value is 5 right there. If I added another 2 pages, I get another one right there, another one right there, until eventually that's all that I can fit on this page. But you can see my row size is only 11 bytes. Remember, I can hold 8,060 bytes on a page. So that's a lot of rows that I can actually get. That's over 700 that I can have before my root page will need to split, and then I have an intermediate level in a new page. And we get layers within our indexes, but only as our indexes grow. Buck Woody, really brilliant man who works for Microsoft, said that if your table is less than 1,000 pages, you don't need to re-index it. I would listen to him. Really, really great maintenance scripts out there by Ola Holmgren, by the Midnight DBAs, Sean and Jen. All of them have the capability to be able to look at your indexes, and you can set a page limit on it. Don't re-index anything under this number of pages. Great, great stuff. So let's do a little bit more, because one of the things I want to make sure people understand very well is the concept of rebuilding indexes. We're going to do a DBCC IND, we're going to alter our table, we're going to rebuild, and we're going to do another DBCC IND and see how that affects us. So first up, I get my DBC CIND, and I can see I've got page 281, 83, 84, 85, what we know and what we're used to. And now I'm going to alter and rebuild my table, and then I'm going to do another DBC CIND. And you can see that all of my page numbers have now changed. I have 287, 286, 288, 289, 290. And that's the thing I want people to understand is when I look at a rebuild operation, rebuild is fully logged, metadata as well as any insert, update, delete that I do against my database. In this case, when I rebuild an index, this is like moving apartments. If I want to move out of my current apartment, I've got to maintain my lease here and my new one for a little while. I've got a month where they both have to overlap because I have to pack up all my stuff, move it out of this apartment, put in my new one. When I get to my new apartment, I can drop my lease on my existing apartment. I don't need it anymore. If you've ever rebuilt an index, come in the next day, and your data file grew for your database, and you went, wow, why do I have all this extra space? Well, it's because for a little while, you had to maintain the extra space of one of these extra tables, and your data file had to grow. If you've ever had your log file grow, it's because you have a very big clustered index, big enough that you needed more transaction log space to be able to log the inserts, updates, and deletes as you allocated more metadata pages. So, very important concept for us to understand. Let's go ahead and let's go a little bit deeper. What I'm going to do now is I'm going to create a heap table. My heap table, I'm going to have an integer value, char 3000. This is fixed length type, so no matter what I'm using 3000. Default one character of an A. Char 500. No matter what, it's going to be 500, default character of a B. I'm going to insert 15,000 rows, and I'm going to insert into my ID. I'm basically going to take our counter, and I'm going to insert it here, my char 2, and you can see here's my counter. I'm going to take A, and I'm going to cast I as a number against this, and then B and a number against this, so I can get some unique values in every single one of our rows. The next thing that I'm going to do is I'm going to do a select star from DBCC drop clean buffers, and I'm going to set statistics IO on. Then I'm going to select all from DBO heap, where my ID equals 10. What I'm going to do, I'm also going to include my actual execution plan, and what you'll see is that I get this nice table scan. Ignore the green right there. It's telling me that I could probably get a little bit better query if I had an index. And I can see that to return this one row, I had one scan, and I had 7,504 logical reads, 7,409 read-ahead reads, 0 physical reads. Now, don't let this deceive you. Read-ahead reads use the read-ahead mechanism of SQL Server to do physical reads against the disk. Sorry about that. Physical reads are 0, but these are still physical reads. So I had to hit the disk to be able to pull all these back and put them into memory. So what I'm going to do now is I'm going to set statistics IO off. I'm going to create a primary key. I'm going to create a clustered index on my ID. I'm going to do a DBCC drop clean buffers. I'm going to set statistics IO on. I'm going to select all from DBO heap where my ID equals 10. This time I got a nice clustered index seek. I have 4 logical reads, 3 physical reads. It's a lot better than 7,504 that we previously had. If I want to pull just one row back, you cannot beat a seek operation. It's always going to be better than a scan. Less overhead on your disk, less overhead on your memory. So now let's do a DBCC IND. We're going to do it on our heap one and take a look at it. I've got this ugly graphic up here just so you can see. This is what it's going to look like if you do it on an existing table. A lot of rows are going to come back. I'm going to make this a little bit bigger. What we're going to do is you can see here's my page types. I've got a page type 10. There's my page type 2s. You can see my index level. This is index level 1. Because I have multiple of these, this means that I have at least one intermediate level, and I probably have a root somewhere. We're going to take a look at page 7,806 out of this real quick. DBCC page, and I will pull these values back. It's going to be a nice grid because remember this is our intermediate level just like we were looking at before. And I can see my child pages here. 7,840, 41, 42, 43, 44, 45. My ID key. Remember, we have roughly 3,500 bytes per row, 2 per page. Null because we've got the negative infinity for our first row. And then we've got the value of 3, 5, 7, 9, 11. Now, you can see that my row size a little bit bigger, 14 bytes this time around. Why? Well, because I don't have a primary key constraint. I just have a clustered index. I can have a non-unique clustered index. My primary key constraint would make it to where I don't have to have this thing called a uniqueifier here. A uniqueifier is a 4-byte integer row that pops up whenever I need to make sure that a row is unique. When I could have multiple, because I didn't have a constraint on that integer value. I inserted everything in a loop, so I got unique values, but I could have multiple 1s, multiple 2s, multiple 3s. And if I inserted multiple 3s, I would have the uniqueifier key that uniquely identified this 3 compared to another 3. And I've got an example where I'll show you that just a little bit deeper. I'm going to drop my primary key on my heap, and then I'm going to create a clustered index on DBO heap on my char. And this is going to load slowly, I apologize, but you'll see I get this nice red error. And the reason being is that I need 3,000. I tried to create a non-clustered index on a 300 byte, a 3,000 byte column. Remember, we can only create a non-clustered index on 900 bytes or less. That failed, so now I'm going to create my new non-clustered index on my 500 char column, my char 2. That will create, and then what I'm going to do is I'm going to do a select all from DBO heap where my char 2 is B10010. Looking at my execution plan, what you can see is that I got a nice index seek against my non-clustered index, which is my where predicate value, and then I had to do something called a RID lookup against my heap. It's 50% of the value right there. So even though I'm doing this against a heap, I can still actually get some pretty efficient numbers here. You can see that my logical reads were just 6, a little bit more than my clustered index when I did my where value there, but not that bad. Now, lookup values, if I can eliminate them, I want to. But looking at this, I've got a select start from. I'm not going to do an include column for every column in my table. That would be very inefficient to make a value, an index that's an exact copy of the table just for this query. If I can get rid of a lookup, I want to, because this is additional cost in my query, and it's going to make things more efficient. But you can see this really isn't that bad. That's why I could use that fact table as a heap, because I'll put non-clustered indexes on it if I'm on 2012 or earlier that will satisfy some aggregate queries that I may need as indexes. You can use heaps with non-clustered indexes, and they can be very, very efficient. So one of the things I could do, I'm just going to throw all this up on the screen, is let's say I want to look at my index structure a little bit more. So I'm going to take a look at sysobjects, sysindexes. I'm going to get my index ID back. Here's my heap. It's always going to be ID 0, clustered index ID 1. Your first non-clustered index is typically going to be 2. In this case, it's 3. The reason that it is 3 is when I did my where predicate value, I will create column level statistics if I don't already have them. Anytime I get those nice missing index hints, it's because of those column level statistics. If I use a where predicate value on a column that doesn't have statistics, the optimizer will look at it as it compiles a query plan, and it will say, I don't know what's in that. I don't know how efficient this query can be, and it will create those. And it will give you a missing index hint that says, hey, I estimate that your query could be 90% more effective if you had an index on this particular column. Now, 90 sounds like a big deal, but I've seen missing index hints as high as 5,430. So it's not just a scale of 100. It's one thing that you want to definitely keep in mind. So looking at this, we've pulled back row 451. You can see these are index pages right here, index level 1. Let's go ahead and look at this. I'm going to do a DBCC IND, demo indexes. I'm going to do my file ID, 451, dump style 3. Here's what I get back. I see here are my child pages. Here are my non-clustered index value, B70, 7012, 7026. Here we go. I've got this heap red key we're going to come back to. I can see my row size, 518. Now, on a non-clustered index, I don't care about small, narrow, static, and ever increasing. I care about useful and utility. Kimberly Tripp said something once that I thought was absolutely brilliant. To be fair, Kimberly Tripp says a lot of things that I think are absolutely brilliant. This one stood out to me as I was in regards to indexing. For indexing, she said an index is like a jacket. If it's hot outside, I'm not going to wear a jacket. It's a support structure to help me. If it's cold outside, I will wear a jacket. And that's exactly the case. People often look at indexes that they put in place and they think, oh, I need to keep this index forever. If I have an index that I need for an end of year job, end of quarter job, end of month job, end of process job, I can create that index a couple days beforehand and then drop it at the end of the job. So that way I'm not maintaining the index all the time. If it's hot outside, I'm not going to wear a jacket. I'm going to wait till it's comfortable, it's cool, then I'll put on my jacket. Part of that overhead that you get if you create a non-clustered index on Heap is this heap rid. That lookup value that we had, I have to uniquely find this data, that select star data, and I have to look it up. So what I'm going to do is I'm going to break this out a little bit. We're going to grab one of our columns, and we're going to take this heap rid value, and I can't take credit for this. Keelan Delaney did this a long time ago in a blog, but I'm basically going to take this hex, I'm going to convert it to some substrings, and it's going to give me a specific page ID. The page ID it's going to give me is 9095. Throw all this up on the screen real quick so I can let it load. I'm going to do a DBCC page for page 9095. And if I go down to slot 1, I'm going to find value B704. And keep in mind, that's what we were looking at. Our child ID, our child page for our non-clustered index was 585, and it had value B704. But to be able to find this, I had to take this heap rid, I had to break out the hex, I had to look at the page number and the slot as well as the file, and then I had to go and find all the supporting data for B704 from this page. That's a lot of overhead. Anytime I have a lookup that I can eliminate, I want to eliminate that. And the query plans don't always show you the most effectual use of those. I have seen query plans before where it said that the lookup was actually 0% of the overall cost of the plan, and by getting rid of that lookup, I saved about 20 minutes on a really long running query. So I'll play around with it. Sometimes you can find hidden gems like that, not always. Query tuning is a little bit of an art, a little bit of a science, but whenever I see a lookup value, if it's one that I can readily avoid, I want to try and do that. We're running low on time, so I'm going to try and blaze through some of this as much as I can and get to questions. I don't think I'm going to be able to get to the fragmentation demo that I had wanted to do for you. So next up is a unifier. I'm going to create a students table, and I'm going to load a lot of this. This is just going to be all unique data. Again, you can grab these slides from my blog. And what I'm going to do is I'm going to create a clustered index on the column first name for DBO students. That's going to give me a lot of repeating values. Remember, a clustered index doesn't need to be unique. A primary constraint needs to be unique. I'll do a DBC CIND. I'm going to get page 2048, and I'm going to break that down, and I'm going to get this intermediate level page so we can take a look at it. You can see here's all my child pages, and my first name, the key value, is Paul. And you can see these unifiers are beginning to add up. And they're adding up because I have a lot of different Pauls in the database. So when you get a unifier, a non-unique clustered index, you will be adding overall size to your row size. Where this can really start to help you is with capacity planning. If you're doing capacity planning for a system, you can mathematically say, here's the number of rows I've got, here's the number of bytes that I'm looking for these index keys, and you can begin to say this is how much I can actually get on a page. It's a very effective way to be able to say, based off the numbers I believe we're going to have in this database, this is how large this is going to get. And then you could increase the scale by 20%, 30%. Say, here's what we believe our year-over-year growth is. It's a great way. Does this hardware need to last us 3 years, 5 years? And then you can go, oh, well, you know, this is my ballpark of how much space we need for this system. This is how much physical disk. That was index internals. So I've got more that I wanted to do on making good changes and bad changes. The time that it's taking to let all this load, I'm going to try and run and stop a little bit for you. So how do we measure performance? What you want to do is you want to look at set statistics IO on, set statistics time on, seeks versus scans, and your actual execution plan. Those are going to be your key metrics for being able to determine good index performance. So let's make some good changes. I'm going to create my college database again, and that script is in the indexing script for this. And I'm going to do a lot of screenshots of creating that so you can see it. But don't worry about walking through that code. You've got it. Needless to say, I'm going to create a students table, a courses table, an enrollment table, and a grades table. Then what I'm going to do is I'm going to say set statistics time on and IO on. I'm going to do a DBCC drop clean buffers. Don't do this in production. This is a dev thing because it will drop everything out of my memory so I can read from scratch what I'm actually doing. Every time you run a query, if you run it once, it takes a little bit longer. You run it a second time, it's faster. The reason is you've loaded all of those pages into the buffer pool. They're sitting there in data cache, and you can access them readily. Your memory operates in nanoseconds. Your CPU operates in nanoseconds. Your spinning physical disk are milliseconds. If you're lucky enough to have SSDs, they're microseconds. They're a factor of 1,000 times faster than your millisecond disk. But your millisecond disk are a factor of 100,000 times slower than your memory, which is why things go a lot faster after you run the query once. So we're going to say select first name, last name, social security number, birth date from students, where SSN is this right here. This is your SSN. Don't tell me. I generate all this randomly. I'm just kidding. Social security numbers don't start with 9, so you should be safe. I'm going to include my actual execution plan, and you can see I get this plan back. It's telling me there's a missing index. I've got parallelism. That's what these little things right here indicate. And I can see that to be able to satisfy this query, to get this one social security number applicant back, I had to do 6,402 logical reads, 3 physical reads, 5,817 read-ahead reads. And my execution time was 124 milliseconds. Elapsed time was 129. Parallelism is why this is a little bit more. So what I'm going to do is I'm going to create this missing index that I've got right here. That missing index would have said create a non-clustered index on SSN. It didn't have a non-clustered index on it, so I had to scan the entire table. So what I'll do now is I've created my index. I'm going to see what effect this has on my query. So we'll set statistics IO and time on, do drop clean buffers, because we want to understand from scratch how this is going to affect our query plan. We're going to say select first name, last name, SSN, birth date from DBO students, where SSN equals same SSN as beforehand. What we will do is we're going to include our actual execution plan. We've got a non-cluster, a nice index seek, and we've got a key lookup. Key lookup's 50%, but we immediately cut this down to 6 logical reads, 3 physical reads. Our CPU time is no longer parallel, is 0. Our elapsed time was 39 milliseconds. We could do better. What we're going to do now is we're going to create this column because we've got a subset of columns from the student table. There's more columns than this in there. We're going to create a covering index. So we're going to drop our index. We're going to recreate our index on SSN, and we're going to include first name, last name, and birth date. Then we're going to go back, set statistics IO and time on, DBCC drop clean buffers, first name, last name, SSN, birth date from DBO students, where SSN equals this. Include our actual execution plan. You can see we've got a nice index seek against our non-clustered index. We had 3 logical reads, didn't even register for physical and read ahead, and we didn't even register in milliseconds for our query. We are now a sub-millisecond query for 129 milliseconds. If this ran once a day, not a big deal. If this runs 1,000 times a minute, we just saved a whole lot of CPU on our box. So what I want to do next is define column definition. I'm going to create a little bit different table, and I won't sit on this too long, but I want you to be able to see it. I'm going to do my table 1, my ID, my date, my char 1, my first name, my last name, nickname. I've got a filler that's a text field, and then I'm creating a composite primary key clustered index, my ID, my date, my char 1. Insert a lot of data. And one of the things you can see is I'm going to create a non-clustered index on this table, and I'm going to put my ID, my date, my char 1, part of my primary key. I'm going to define it my non-clustered index because I have queries that use it, and I just wanted to throw everything on my non-clustered index. My first name and my last name. Now, these columns are going to suffer. The further away you get from the top defined position, the less likely you are to get a very, very performant query. So notice these changes here. So running through this, I'm going to do a DBCC drop clean buffers, IO on, time on, select my ID, my first name, my table 1, where last name equals Ball, first name equals Bradley. You can see that this is 4,637 logical reads, and it's an index scan. Because this is so down on my index, I can't get a seek off of this, I can only get a scan. 100,558 read aheads, my execution time, 203 milliseconds for CPU, 230 for elapsed. Next up, I'm going to do a select first name from my table 1, where my ID is between 8001 and 8020. This is a good one. I get this back really quickly. It's a nice non-clustered index seek, but I'm using my ID. That was defined up front. I should expect that I would be able to get this. Looking at this, I've got my first name, my last name, my date, my nickname from my table 1, where my first name equals Bradley, my last name equals Ball. You can see I've got a key lookup. The key lookup is 0% of my issue, though. My index scan is 86% right here. My nested loop join is about 14% sticking this together. And I can see that my logical reads 4,697, 4 physical, 4,664 read ahead. And it looks like my CPU time is about 218. My elapsed time is 500 milliseconds. Not very efficient. So let's change this. What I'm going to do is I'm going to take out the clustered index portion. Any of those queries will be satisfied by my clustered index. I want my non-clustered index specifically for first name and last name. I want to move these columns more up to the front of the queue, so to speak. I can see on my query where I was saying select my ID, my first name, from my table where last name equals Ball, first name equals Bradley. I was able to reduce this to 4 logical reads and get sub-millisecond execution, whereas before I was in the thousands of reads and my CPU time was around 203 milliseconds. If I look at my old execution plan as well, I can see I used to have an index scan, and now I have a nice index seek. Each of these things are going to help me find indications, but sometimes they're a little bit tricky. When I do my first name from my table 1, where my ID is between 8001 and 8020, it doesn't look like I gained a lot. My old one on a non-clustered index was 4 logical reads, 3 physical. My new one on a non-clustered index, or going against my clustered index, are 4 logical reads, 2 physical. And I can see from my execution plan that I just went from an index seek to a clustered index seek. So I dropped these columns from my index, but I didn't have a performance suffer. And I need to check both those IOPS, and I need to check both the execution plans to validate that. When I look at my last one that we did, DBCC drop clean buffers, my first name, last name, my date, my nickname, from my table 1, by first name and last name, my old logical reads were 4,697. Physical reads were 4. Read aheads were 4,664. My CPU time was 218 milliseconds for a total elapsed time of 571 milliseconds. I got that down to 64 logical reads with 3 physical reads and 16 milliseconds for a total elapsed time of 204 milliseconds. Less elapsed time than my CPU spent last time. Looking at my execution plans for these, it almost looks a little deceiving because it looks like my key lookup costs went up 50% versus 0. Looking at this closely, I can see instead of an index SAN, I have an index seek. And in this case, if I just closely glanced at this, I may have overlooked some of this. But it's very important to understand that looking at my IOPS, this is a huge benefit. So whenever I look at an index change, I want to measure what that overall index performance is. We are just about out of time, so the big things that I want to make sure people understand is how to get some good information. My buddy Jason Straight, Jason's a Microsoft Certified Master, Microsoft MVP. He wrote SP Index Analysis. It's a fabulous script. He wrote the book literally on indexes. His 2014 index book's coming out, and he should have a script up for 2014 pretty soon. I'm going to be looking that over for him pretty soon. So if you get a chance, go to jasonstraight.com, take a look at his index resources. It's a really fabulous script to be able to help you manage your environment. Remember Ola Holmgren's script and the Midnight DBA scripts as well for maintenance. My resources page on my blog, you'll be able to get the indexing scripts from there. And I thank you very much. And sorry, it seems like we had a little too much content to be able to cover within an hour. But thank you very much for coming today.
That's great, Bradley. I think that's fantastic. Is there any questions you want to answer real fast, or?
And I apologize. Maybe I'm not seeing them, but are there questions? Because I thought I had the chat window open. I didn't see any of them.
It's in the questions window, actually. So if you look in your toolbar, you should see right above the dashboard a questions window. Do you see that?
I do not. I see webcam, audio.
That is so
attendees.
strange. That's very strange. Okay. Is there a way to avoid clustered index scan?
The only way to avoid a clustered index scan is to actually search on the key and have a subset of the range of values, so you can get a seek operation. If you get a clustered index scan and you're looking for 80% or more of the table, you're going to get a scan every time, and it's just the nature of it.
Okay, fantastic. How many percents of data retrieved from a non-clustered index will the SQL Server will do a scan instead of a seek?
It's around the same threshold. It's right around 80%.
Okay. If my ID is the column index, CI column, it's redundant in the non-clustered, the NCI. Is that true? False?
Is that? Oh, sorry.
If my ID is in
the clustered.
Yep.
Oh, I got you. I got you. So it depends on whether you define it or not. If my ID is the clustered key value, and let's say that's our only clustered key, and then I create a non-clustered index, if I do not define it, then anything I define in that index is searchable. It's in my intermediate level. I can actually search down for it. But if I search for my ID as my where predicate value, it won't use that non-clustered index unless I define it as my ID and my char. So it's got to be included in there to be part of that searchable column. And whatever you leave within your where predicate value is going to push the optimizer in the direction. So if I have my student ID and my social security number, my social security number is non-clustered index, my student ID is a clustered index. If I search for a student where student ID equals something, I will use the clustered index, unless I define my non-clustered index as my ID and social security number. The optimizer will look and choose what the least cost plan is, and then it's more determined on the number of rows. If I'm pulling back everything, it's going to use the clustered index. If I'm pulling back just my student ID and my social security number, it will use the non-clustered index. Does that make sense?
I believe so. Hopefully that does for the user. How do included columns get stored in the index? Why does adding columns to IX matter more than adding them to included columns list?
Absolutely. So included columns allows us to get past the 900 byte limitation, but they are only stored at the 0 level leaf value of the non-clustered index. So they're not searchable, and I cannot search on them. Just like if I don't define the clustered index is down there at level 0 as a pointer. So if I said select my ID and SSN is my only column that I've defined in my non-clustered index, I'm not going to have to do a lookup value for my ID. But if I've got my ID, SSN, and birth date that I need for the query, and I'm searching on SSN, I need to add birth date as an include column for it to be stored at that 0 level. Otherwise, I'm going to have to do a lookup value to get birth date.
Okay. Here's a quick question on fill factor. What happens when the page goes past the fill factor and gets full? When does the page split?
So you can go up to 100%, and you split at the point in time that you try and insert a row, and there is not enough free space to be able to put that row onto that page. We have PFS pages, page free space pages, and they track the percentage of free space. And then there are some header values within the page themselves that says the number of available bytes on the page. And so essentially SQL Server knows whether or not it has room to be able to put the value on the page. If it does, it puts it on there, even if it goes past fill factor. The only thing that fill factor does is whenever I rebuild an index, I will always rebuild it back with the same fill factor in place once I set it once. So remember setting for a table. So by default, fill factor is 0. We fill pages up to 100%. And then if I rebuild something at 80, it remembers it, and that table in and of itself stays at 80 until I override that fill factor number and I set it to something else.
Fantastic. Bradley, thank you so much for joining us today. We really appreciate it. And just a reminder, everybody, this webinar is recorded and will be available on the website later. If you have additional questions, please reach out to Bradley directly. Everyone have a good day. Thanks. Bye, Brad.
Thanks, everyone. Thank you. Bye-bye.